I'm Changyu from Our Next Energy. So I'm gonna talk about our progress on calibrating the model by using GT. In particular, I'm going to present a LFP graphite cell calibration with focus on hysteresis effect. Before really introducing the model or the project, I want to start with what our company is doing. So we are based on a fact that the materials we typically use in the batteries are not abundant on Earth. So you can see on the left figure that the manganese, nickel, and cobalt, especially the nickel and cobalt, they are not sufficient in the Earth. As a result, their costs will be much higher than the ion-based cathode, which you can see in the middle figure. Another perspective, we are a little bit afraid of nickel and cobalt-based cathode is their chemical structure, which causes them to have self-heating effect during thermal runaway. As you can see on the right figure, when the temperature rises, there will be a self-oxidation effect, so that the self-heating effect of the cathode will be much more severe than ion-based cathode. So that's caused a problem in the battery safety. So after promoting the advantages of ion-based cathode, what we are doing is to build LFP cathode or LFP cathode-based batteries. One of the products, as you can see on the left, is Aries, which is a graphite cell used in commercial vehicles. And also on the right, Aries 2, this product we're under development with higher energy density. So in the middle, I'm showing a pack level energy density, volumetric energy density. So because LP has a higher safety standard, we do not need to put so much, for instance, the buffering materials inside the package, so that the cell-to-package ratio is pretty high. As you can see in the middle figure, that the volumetric density of LP is actually higher than nickel or cobalt-based cathodes. So our mission is just to double the range of the EVs to increase the safety by try to reducing the nickel and cobalt-based materials, and also to develop a sustainable chain to create a North America-based cell and material supply. So as I mentioned, Aries is one of the products we have. Of course, we have more products. So what I'm going to introduce today is the one of cells we are using. As you can see in the screen, the one we are using is just this prismatic cell with graphite as anode and LFP as cathode. The capacity is pretty large because it's a large cell, over 200 ampere hour. And the right figure is the teardown pictures. So the goal today, or the project I'm presenting, is to model the cell for cell design and BMS purpose. To model the cell, there are a few options. One of them is a physics model, and the other is equivalent circuit model. I think the Mr. Milano already advertised for us the advantages of physics-based models. I'm going to list another few advantages. For instance, predicting the different cell designs, calibrating after calibrating model, we are able to know the cell potential and current distribution in the 3D geometry. And also, we are able to develop some physics-based aging diagnosis. For instance, SEI growth, CI growth, and cracking of the cathode, etc. And the last one is to couple with other models, for instance, the thermal model and mechanical model. So our goal is to, in this project, is to develop physics-based model from GT to build a digital twin of the LP cell. And the steps I'm going to present today include these four parts. The first one is to input the geometric data of the cell. The second is to fit for the OCV data. And third is to fit for the dynamic parameters. And the fourth is to get the HPC data into the model, which is only used for validation. It's not used for fitting. The first step is pretty easy, which is just to input the geometry information. As you can see on the left, we are just measure the geometry data of the cell and then input into the GT model on the right. And this is a very straightforward step. The second step, after we obtain the geometry information of the cell, we need to get the balancing of the two electrodes. So what I mean by balancing, probably also Mr. Mallow also talked about this, is to get the stoichiometry numbers where these two electrodes start when we have 100% LCC, and also where these two electrodes ends when we have 0% LCC. So in particular, we have the four primers in the simulation primers, the graphite at 0%, graphite at 100, and LFP at 0%, LP at 100. So in Mr. Milano's presentation, they were X up, X low, Y up, and Y low. And another parameter we have is the capacitor loading. So we want to know how these model correlates to the 228 ampere hour capacity. The experiment here I'm using is on the top left is a continuous discharge and charge curve, a very small current, silver 50. On the right, we can see that the strategy here I'm using is a little different from what Mr. Minal presented. I'm not using the full charge capacity or discharge capacity. I'm just using an override cell balancing function to directly input these four parameters. And of course, the outcome should be the same, which means what we want is that the simulation result should be similar or better to be the same as the experiment. One thing I want to highlight here is the hysteresis function in the GT all-line. So as you can see on the right side, when we charge and discharge the cell, although we only use a very small current, we can see two distinctive curves that was caused by the hysteresis effect of the materials. Both for graphite and LP, they both have the hysteresis effect. I think, but the LP is more dominant. As you can see on the left, so we just input this feature into the model to have this hysteresis effect in LP OCP. When we have the voltage half cell potential of LP, we have different curves for the voltage with respect to the stoichiometry numbers, so that the hysteresis effect can be integrated into GT. So this slide shows the results after getting the five numbers in the simulation. And you can see on the right, the simulation has a pretty good match with the experiment. In particular, what I like is the features in the simulation. What I mean by features is the transition of the plateau. So the SOC corresponding to this transition match with the experiment as well. Although we can see some discrepancy at higher SOC, I think it's mostly because of the nature of the OCP, because we are using some literature values for OCP, not the experimental results. So there might be some difference between the literature materials and our own materials. But in general, I think we had a pretty good fit with less than 20 millivolts error in the middle, not including the high SOC region. After getting the balancing, what I want to do next is to get the dynamics. By dynamics, what I mean is to discharge or charge the curves, the cells at different rates and temperature. So in experiment, what we have is the discharge curves at different rates and temperature. The temperature includes 10, 25, and 40 degrees Celsius, and the rate includes silver 3, silver 2, and 1C. So we are not going to use all the temperature curves, all the discharge curves as our fitting. What we put here is only silver 2 at 10 degrees, silver 3 at 10 degrees, and 1C at 25, and silver 2 at 40. Other curves are used for validation. In terms of simulation or the parameters we want to calibrate in the model, includes the anode particle size, the cathode particle size, and also the heat transfer coefficient to calibrate the thermal effect, and also the initial SOC. The reason we include SOC is that although in the experiment we design every cell to be discharged at 100% SOC, we know that there are some slight difference when we charge the cell. So we allow the initial SOC to be slightly changed in the model to allow this parameter to be changed. And similar to OCV fitting, these dynamic parameters should be tuned to match the rate curves. One thing I want to highlight here is the simulation, the optimization package or function in GT. So what I did, as you can see on the left, is just to input these 4 parameters in the model to serve them, to use them as the fitting parameters. And my objective is the difference between the experiments and the simulation. And the right figure shows the interface. When we fit for the data, we can observe the trend that as we have more designs of the cell or more set of the parameters of the cell, the difference between the cell simulation and experiment is decreasing. That's something we want. And then I'm going to show the results for dynamic fitting. I'm going to show the 10 degrees Celsius result in 40 because the room temperature is pretty easy to fit. So I'm just omitting it here. The black one denotes the fitting data, and the blue one denotes the test data. So if we start from the right one, which is 40 degrees Celsius, we can see a pretty good match. The simulation and measurement are almost the same. And the average error is less than 20 millivolts. But on the left-hand side, at low temperature, we do have some difficulty here. As you can see that maybe only the middle one, the silver 2, has a pretty good fit with about 29 millivolts error. But the top one, the relatively low discharge one, and also the high rate one has a relatively large error, about 70. So in general, I think the curves match well at high temperature, also at room temperature, but slightly worse at low temperature. That's something we want to improve further as our future work. The last one, the first step, is the HPC data. So as I mentioned, we're not going to use HPC to fit for anything. We just use it as the validation step. For those who don't know what HPC means, it's just a short term for hybrid pulse power characterization. Basically, the idea is to use different curves to different currents to excite the cells and observe the voltage response in terms of how the impedance changes with respect to current, and also how the cell relax during this short pulse. I would say that at the bottom is the voltage response corresponding to the top current. I would say that in general it was fine, although we do see some discrepancy, especially in these peaks, where the model seemed to underestimate the resistance, and also so that we see a voltage difference as large as 100 millivolts, and also the relaxation of the simulation is faster than what we can measure from the experiment. That's also something we want to improve as future work. Although the average error is probably only 9 millivolts, but we do feel that we need to improve on the peak performance. In conclusion, we just built a PUD model via GT with the following data: OCV curves, the rate test. The rate tests were split into test set and also the training set, and also the HPT test, which was only used for validation. And I want to highlight some features used in GT which helped us to facilitate the calibration, embedded optimization toolbox, the hysteresis effect in OCV, and also its internal material database, because we only have whole cell data in the experiment. So if we do not know the material properties, we rely on the internal material database from GT. Of course, it's an ongoing process. We have some future plans. The first thing is for the capacitance and particle size distribution. This is to help us to match the relaxation period better with the experiment. As I mentioned in the previous slide, the relaxation in simulation is faster than the experiment. So we want to tune the capacity effect and also to have particle distribution so that the fusion of the model will be better or match well with the experiment. And the second one is low temperature OCV. So as I mentioned, our low temperature retest was not that excellent. One of the major reason is the low temperature OCV. We do not have the half cell low temperature data, so that actually the low temperature OCV is still very close to room temperature, which is not true. That's why we want to include this feature with low temperature OCV. The third one is to decouple the impedance by ES. So right now in our rate test, we cannot distinguish between the diffusion resistance and the intercalation resistance. So we just lump them when we tune the results. So as a future work, we want to analyze the ES data to decouple the impedance with, for instance, the ohmic resistance, the charge transfer resistance, the diffusion resistance. Although it won't have an impact on our fitting results, but that will make the model closer to the real physics. At the end, I want to acknowledge Nikhil for his assistance in building the model. Yeah, that's it for my presentation. Thank you.